Good morning, ladies and gentlemen. Today we will be talking about that instrument in the aircraft which measures the forward speed of the aircraft. The name of the instrument is known as the Airspeed Indicator, or in short we call it as a ASI. At all times when we are in the room or anywhere we are subjected to a pressure which is known as the static pressure. The static pressure is the pressure exerted by the column of air which is above us. So irrespective of where you are, you will always be subjected to this pressure, which is because of the column of air which is above you. So the prevailing atmospheric pressure of an undisturbed airflow is what we call it as a static pressure. And another type of pressure what we experience is whenever we start moving. Okay, for example, you are sitting behind your dad's scooter or bike, or you're traveling in a car. Once the car starts moving or the bike starts moving, you will feel the pressure of the air on your face or on your hand and your body parts. Okay, that pressure, what you feel, okay, because of the motion of the aircraft, is what we call the dynamic pressure. So the dynamic pressure is the additional pressure caused due to the aircraft's forward motion. So now the pressure what we actually feel on your face is therefore will be the sum of the static pressure which was already existing and the dynamic pressure which is there because of the motion of the aircraft. So therefore that pressure is what we call it as the Pitot pressure, the pressure produced on the surface when a flowing fluid is brought to a complete rest. So therefore, this Pitot pressure P will be equal to the dynamic pressure plus the static pressure. So now, the aim or fundamental behind this instrument, that is airspeed indicator, is that to find out that portion of the pressure which is there because of the motion of the aircraft. That pressure which is there because of the motion of the aircraft is what we call it as a dynamic pressure, as we discussed. So therefore, the dynamic pressure will be the Pitot pressure, that is the sum total of dynamic plus the static, and the static pressure which was already existing. So therefore, the dynamic pressure is equal to Pitot pressure minus the static pressure. This is the aim, or this is the fundamental behind this particular instrument, that is airspeed indicator. So now let me demonstrate to you that this particular balloon which is tied on this straw is experiencing static pressure, right? So the static pressure outside and the static pressure inside are the same. So therefore this balloon is not inflating or it is not deflating. Let us assume that I started moving, so I will experience some additional pressure, that is because of the motion of the aircraft. So that pressure I'm going to simulate it by blowing it. As the forward motion of the aircraft increases, the pressure, that is the dynamic pressure, is going to increase. So therefore, if the dynamic pressure is increasing, the balloon starts inflating. I start inflating the balloon. So whenever this balloon is expanding, when it is expanding, I am feeding the pressure which is somewhat like the Pitot pressure, which is the static plus the dynamic. When it is expanding against the static pressure which is already existing in the atmosphere. So now automatically when I feed a balloon, in this balloon, okay, the static pressure was already existing, the static pressure was already existing inside. The additional pressure which is there because of my Pitot pressure is now subjected to the static pressure while expanding, so it automatically fulfills the formula, that is the dynamic pressure is equal to Pitot pressure minus the static pressure. Now in this particular balloon, if somehow I connect it to a kind of a lever, this balloon is attached to a kind of lever. Whenever it expands, this lever is going to move like this. Whenever it contracts, it will move like this. Whenever it expands, it will move like this. So thereby, if I put a gear on top of it and then make it drive a needle, that particular needle will show the airspeed. So this is the working principle of a ASI, or the airspeed indicator. So every aircraft will have the probe which measures the pitot pressure and which measures the static pressure. The one which measures the pitot pressure is what we call it as the pitot tube, and the one which measures the static is generally in larger aircraft it is known as a static vent. So therefore, in this particular aircraft, the pitot pressure is fed through a tube which is facing forward of the aircraft, because it has to measure the pressure which is causing because of the motion of the aircraft, and the fed to the aircraft instrument, that is the ASI. We will have a look at the construction. And the static vent similarly goes through a tube to the instrument. The basic principle of operation of an ASI is to measure the dynamic pressure and indicate that dynamic pressure in terms of a airspeed, because the dynamic pressure is proportional to the speed. So this is how the pitot tube looks like, which is facing in front of the aircraft, and this is how a static vent looks like in any large aircraft. So now the pitot pressure which was coming from the pitot head will be fed inside the capsule. Like I have shown you, this was a balloon. In an aircraft, that thing where the pitot pressure is fed is what we call it as a capsule. So inside the capsule, the pitot pressure which was coming from this pitot tube will be fed inside the capsule, and this is a sealed casing. Sealed casing. In this casing, the static pressure will be fed. So whenever the capsule expands or contracts, it is expanding or contracting against the static pressure. So therefore, we achieve that same formula, that is dynamic pressure is equal to pitot minus the static. So whenever this capsule expands or contracts, the lever is going to move forward or backward. So through a system of linkages, I can connect into a drum where the drum will be rotating. This drum is going to be rotating, and the needle will also rotate. Therefore, any pressure which is felt in this capsule can now be converted into a kind of an indication in terms of a speed. That is the function of an airspeed indicator. Now we need to derive the relationship between the dynamic pressure and the speed of the aircraft. That relationship is half rho v square. So you may recollect when you were studying class 10, 11, 12, you might have learned something known as a kinetic energy. That kinetic energy is that energy which is possessed by a particular substance because of the motion. So when we are talking about the solid particle, it has got a particular mass, isn't it? So therefore the kinetic energy was half mv square. But however, for the air, it does not have a fixed mass, because the mass will depend upon the density of the atmosphere. More the density, more the mass. Lesser the density, lesser is the mass. So therefore, there is a direct relationship between the mass is proportional to the density of the air. So we can replace that half mv square in that formula of kinetic energy by the density. So therefore it comes, the dynamic pressure is equal to half rho v square, where rho is the density of the atmosphere. As we all have seen in our instrument classes, that the calibration of all the system, that is of all the instruments which are there inside the aircraft, is calibrated under the standard ISA condition. ISA condition wherein the pressure is 1013.25, temperature is plus 15 at the mean sea level, and it will be calibrated for the density at the mean sea level. So therefore, this instrument ASI is also calibrated considering these standard conditions. So now, as we have seen in the formula, that the dynamic pressure is equal to half rho v square. So therefore the change in the dynamic pressure with respect to the velocity of the aircraft or the speed of the aircraft is with respect to the v square, not with respect to v, velocity alone. So whenever I have to calibrate this system, I have to keep it in mind, it is not the kind of a linear graph. Since it is not a linear graph, because it depends upon the velocity square, we will have to calibrate this instrument slightly differently. We will have a look. So now if you see in this particular diagram, the gap between 0 and the 50 as compared to 50 and the 100 and 100 to 150, 150 to 200, the gap is steadily increasing. So this is done in order to keep that dynamic pressure is equal to half rho v square. At the lower speed, I indicate move the needle a little bit. As the speed goes on higher and higher, I'm going to be feeling a lot more pressure. So therefore, I need to compensate by increasing the gap between the calibration in an ASI. So the disadvantage of this kind of a system is that at lower speed, when it is very, very critical that my aircraft close to the stalling speed, the calibration area is so small that it will be difficult for us to read the speed. So difficult to read the critical speeds at the low range. So the aircraft stalling speed is very, very low. So therefore, at this particular speed range, my ASI is gonna move a little, and it will be difficult for us to read the instrument. Wide speed range is difficult to accommodate because as the speed indicate, I'll have to keep expanding the gap between two particular numbers. So this particular instrument will be limited to a slower speed aircraft. As the aircraft speed is increasing, the gap has to increase so much that in one particular dial, I will not be able to feed the entire range of the aircraft speed. So that's the disadvantage of the simple calibration, okay, which is called what we call it a square law compensation in this particular indication only. Now let's move further to another advanced system wherein the square law is compensated by the rocking mechanisms. Like suppose in this particular diagram, if you see that this is the capsule, when the capsule is expanding or contracting, what is going to happen is if I put a kind of a lever here and I have to push this lever up and down. When I push this lever as up and down, as you can see, it forms a kind of a triangle. When it was at the neutral position, the distance from this place to this place is as compared to the distance between this place to this place. So therefore, when the capsule expands in the neutral position, it will be the distance from here, which is lesser, but as the capsule expands, this particular point which is pushing that lever is going further away from this. So therefore, if you learn the arm movement, okay, if you see that in order to move a smaller amount of angle here, this particular arrow has to move a larger distance. So that capsule, for a larger expansion of a capsule, it is indicating a smaller kind of a speed range. So therefore, as the speed increases, the capsule expansion increases, the arm length also will increase. So therefore, it is automatically compensated by this kind of a mechanism. Another mechanism which is commonly used in the aircraft is that instead of having a kind of a mechanism like this, in a particular dial, he will have a slot which is generally known as the banana slot, wherein when the speed ranges are very, very low, the push onto the needle is going to be affected from this particular area which is very short arm, but area which is short in terms of arm, but as the speed is increasing, this particular rocking arm which was there to push the needle is going to be pushed further away in this banana arm, thereby increasing the arm length. So the motion for a particular amount of expansion, that is for more expansion, I will have a lesser amount of movement onto the needle. This is how the square law of speed is compensated in a ASI or the airspeed indicator. The another mechanism what we use is the kind of a spring law, okay, wherein when the capsule is not expanded and if it is expanding, the first restriction it is going to felt is by this screw. So therefore, the tension on the spring is going to be very, very less and the needle will indicate normally. As the speed is increasing, the it will touch with this particular screw and thereby increasing the tension on this spring. The length of the spring here is shortened now. So since the length is shortened, the tension in the spring is gonna increase. So therefore the capsule has to push further, because as the dynamic pressure increasing, the capsule was expanding more. So this has been restricted by this spring. So thereby, and thus it will have multiple spring to resist. When the aircraft is at very, very high speed, the arm length has been reduced so much that when the capsule has to expand, it has to go through that kind of an increase in the tension. So therefore, the problem of the square law is also compensated like a mechanism like this, which is known as a ranging screws. Thank you, ladies and gentlemen. If you have any questions or any queries, you can directly put it onto the comment. And once again, if you're watching it for the first time, kindly subscribe, like and share it to your friends so that they also can benefit from this class. Thank you very much. Have a nice day. So now let's have a look at the errors of an ASI. What are the errors? The first error is every instrument what we have will have some instrument error. The instrument error is that error which is caused by the mechanical imperfection or the manufacturing tolerances while making the particular instrument. This can be determined during the test flight and find out in the wide speed range, and the correction can be given for this particular error. Now the next error is occurred because of the incorrect positioning of the static vents. At all times, if you imagine that the static vents, if you see, was at the side of the aircraft, it is supposed to measure only the static pressure. However, as the aircraft is always moving, this static vents, if not positioned rightly, will all be influenced by the dynamic pressure. So when it is influenced by the dynamic pressure, some part of the dynamic pressure will be felt or will be fed through the static pressure, thereby causing error onto that instrument. That error is what we call it as a pressure error. The pressure error will depend upon the position of the pitot head or the static vent, and also depend upon the speed of the aircraft. As the aircraft speed is increasing, changing, there are always some kind of a turbulence which is around the aircraft. That also will influence the accuracy of this. And it will also depend upon the angle of attack. When the angle of attack increases, as we have learned, the flow around the aircraft changes. So whenever the flow around the aircraft changes, there may be some amount of infiltration of this dynamic pressure onto the static vent. Because of this, it may give rise to a particular error. At lower speed aircraft, that is in a larger aircraft, in a transport aircraft, the static vent is generally separated from the pitot head, like the picture what we have seen. The pitot was somewhere at the front of the aircraft, and generally the static vents are generally in the side of the aircraft. Okay, in a very high speed aircraft, the pitot-static head is generally away from the aircraft. If you would have seen most of the fighter aircraft, this is the nose of the aircraft. You have seen a kind of a probe which is protruding out of the aircraft. That probe which is protruding out of the aircraft nose is your pitot-static tube, wherein it is separate from the fuselage, so that minimum disturbance from the fuselage is there or the airframe is there. That is why it is placed away from the aircraft structure itself. And this particular error can also be determined during the test flight, and the correction can be printed and kept inside the aircraft as a pressure and the instrument correction card. The instrument error, as we discussed, can be found out during the test flight. Similarly, the pressure error can be found out in the test flight, and the error combined together can be printed and kept it on the aircraft in a card which is known as a PIC card. So therefore, IAS, which when applied these two correction, okay, that is the instrument error correction and the pressure error correction, give the speed what we call it as a rectified air speed. The another error what we experience is compressibility error. What exactly is compressibility error? When we say in the ISA definition that air is incompressible. But however, we all know that air is a compressible fluid. So therefore, the in while calibrating, what we used was the calibration formula was used in the standard atmospheric condition at the mean sea level values. So at higher altitude, as the density becomes lower and lower, as we go higher and higher, the density becomes lower and lower. So therefore, the air is more compressible. It is easily compressible. Okay. So because if it is compressed, what is going to happen is it is going to give me a greater dynamic pressure. So therefore, because of this compressibility error, your ASI will be overriding all the time. So now this rectified airspeed, what we have talked about, which when applied by this correction, that is the compressibility error correction, that is what we call it as a equivalent airspeed, or in short EAS. Density error, again, once again, all the calibration was done on the mean sea level, considering the density at the mean sea level. Any deviation from the standard condition, which was assumed, will give rise to the error in the ASI. That error is what we call it as a density error. So now, density error decreases with the altitude. So now, EAS, which when applied the density error, which is the under root of the density at any altitude, this is a density at any altitude, this rho, upon density in the mean sea level, if we take the under root of this ratio, this is what we call it as a correction for the density. The equivalent airspeed, which when corrected by this for this density error, is known as the true airspeed. Actually, the true airspeed is what is going to be the speed of the air particles around your aircraft fuselage or the aircraft. So therefore, when we talk about this, the true airspeed is the actual motion of the aircraft with respect to the air which is surrounding. That is why we call it as a true airspeed. I repeat, the true airspeed is that motion of the aircraft around with respect to the air which is around it. So that is why we call it as a true airspeed. So the equivalent airspeed plus minus the density correction is going to give me the true airspeed. So therefore, we'll have a look at the different types of the speed what we have learned so far. That is IAS, indicated airspeed, which when corrected with instrument error correction, and the pressure error correction will give you the RAS, rectified airspeed, or in some other word it is also called as the calibrated airspeed, CAS, calibrated airspeed. The CAS or the RAS plus minus the compressibility error will give the equivalent airspeed, and the equivalent airspeed plus minus the density error correction will give you the true airspeed. So another error which happens in the ASI is because of the blockages or the leakages, because all this pressure was vented through a pipe or a tube. So therefore, any blockage or any leakage on these pipes is going to give the errors in the ASI. So we will talk about the blockages first. And if the pitot is blocked, what is going to happen? It is not going to sense the variation in the dynamic pressure. Let's take an example that this aircraft was already flying at 100 knots. Because of icing, the pitot is blocked. This particular air which was there inside was trapped when I was flying at 100 knots. So therefore, it will show that 100 knots irrespective of the where the aircraft is accelerating or retarding, basically because there is no further changes in the pitot pressure which has been fade. So as long as you are flying at the same level, the aircraft speed will be frozen at 100 knots. So therefore, if in a level flight, there will be no change in the speed irrespective of whether you are accelerating or retarding. So now with this same condition, if you start climbing, the aircraft was indicating 100 knots, okay, when it was blocked, at that point, let us assume that the aircraft was climbing. From this point onward, the pitot pressure which is being fed is being trapped. As the aircraft climbs, the static pressure is going to reduce as the atmospheric density is reducing there. So the Pitot, which was dynamic pressure, is, remember, is equal to Pitot minus static. This Pitot is constant now because my Pitot is blocked. As the aircraft climbing, this portion of static which is subtracting from this Pitot is going to be reducing gradually. So therefore, whatever the speed, it was indicated in that example, I was saying that it was indicating 100 knots. So if I am subtracting lesser and lesser static, what is going to happen? This dynamic pressure is going to be slowly increasing. So in a climb, if the Pitot is blocked, the instrument will overread. Similarly, if the aircraft is on a descent, the static pressure is going to increase steadily as the atmosphere becomes denser and denser. So if the static pressure which is being subtracted out of that constant Pitot is increasing slowly, so what will happen? The dynamic pressure will drop. So therefore, on a descent, the ASI will underrate. So let us assume that now the static is blocked. If the static is blocked, it is gonna subtract a constant amount of static from that formula once again. Dynamic pressure is equal to Pitot minus the static. Okay, now if the static is blocked during the climb, from the same formula, dynamic pressure is equal to Pitot minus the static pressure. The static pressure which is there inside the aircraft was trapped now because it is blocked. What is happening to the outside the aircraft? The static pressure is reducing outside the aircraft. So it is supposed to be subtracting a reduced amount of static because the atmospheric pressure is reducing. So therefore, it is supposed to subtract a lesser amount of static, but however it is subtracting a higher amount of static because the static was blocked at the lower level. So therefore, your airspeed indicator will underread. The opposite happened during the descent. During the descent, what is same formula? Dynamic is equal to Pitot minus static. This static is now blocked. As you descend down, the static pressure is supposed to increase and the higher amount of static pressure is to be subtracted from Pitot pressure, but however you are subtracting lesser amount of static. So therefore, the dynamic pressure which is being there is going to be indicating higher. So during the descent, the ASI will overread in case the static is blocked. If there is any leak, as you can see in this particular balloon, that if I am supposed to blow, it is expanding. If I am blowing like this, half is leaked. It is not giving that amount of dynamic pressure. So therefore, it always underreads if it is leaking on the Pitot. If the static is leaking in the unpressurized compartment of the aircraft, leaking in the unpressurized compartment, if you are flying a smaller aircraft which is unpressurized, in that the static is leak inside an aircraft, okay, the pressure which is there in the cockpit is going to be lower. As you feel on a car, if you start opening the window of the car and start driving, the air is being sucked out of the car inside. The pressure inside the car is going to be slightly lesser than the pressure outside the car. Similar thing will happen on the aircraft. In the cockpit, the pressure is going to be lesser when the inside the cockpit, if it is open cockpit, unpressurized cockpit. So therefore, I was supposed to be subtracting dynamic is equal to Pitot minus static because it is leaking at the unpressurized compartment. The static which is being subtracted lesser. So therefore, dynamic is going to be more. So therefore, your instrument is going to be overreading. If it is leaked at the pressurized compartment, what is going to happen? Inside the pressurized compartment, the pressure of the inside the compartment is much higher than the pressure outside the atmosphere. So now in the same formula, okay, P minus static, I am subtracting more of a static, so I am going to be having a lesser amount of dynamic pressure. So therefore, my instrument will underread. With this, we will finish the class on the ASI. Thank you, ladies and gentlemen. If you have any questions or any queries, you can directly put it onto the comment. And once again, If you're watching it for the first time, kindly subscribe, like and share it to your friends so that they also can benefit from this class. Thank you very much. Have a nice day.